Let's get started. Thank you all for coming. So my name is Luis Marribas. I'm a project scientist at University of California in Santa Cruz. I will be speaking later in the week, but I'm chairing this session. So we will have two talks now, cosmology and circumgalactic medium. And our first speaker is Matt McQuinn. Matt is a professor at the University of Washington in Seattle. And he will be talking about cosmology, but he has been working on many other different things, and I encourage you to talk to him this week. He knows a lot about a lot of things, in particular CGM, intergalactic medium, large-scale structure, and all things related to cosmology. So take the opportunity. And yes, I'll leave you with Matt. Thank you, Matt. I will be giving you.
Awesome. Oh, thanks for the really kind introduction, and it's a pleasure to be here. I should definitely have this on, right? Okay, I'm a bit of a pointer, and the mouse is not displaying, so I'm going to try to point by describing. But yeah, I'm talking about FRB cosmology, which is a topic where we're trying to figure things out, and I think that's going to be apparent from this talk. But we have two things that we think are potentially interesting about using FRBs as cosmological probes that make them unique. And one which is much better developed, and you're going to hear a lot about this week, is that they're sensitive to very diffuse baryons via this effect of plasma dispersion that was talked about earlier today. And in fact, we just don't have ways of probing low density ionized gas in the universe other than FRBs, and there's also some CMB anisotropies that are interesting here. And so potentially FRBs can tell us about where most of the gas is in the cosmos, which will also be the subject of the talk after this. And that's potentially interesting for cosmology. The second aspect is that they can be exquisitely timed. And they're about as good a point source as you'll ever get. This is even the case if there's millisecond scattering in the host galaxy. And so if we're unambitious, we can time them to a millisecond, but some have started to even use coherent approaches where we're timing their arrivals to nanosecond. But at the same time, precision cosmology is hard, especially for constraining the standard set of cosmological parameters. So FRB cosmology is going to be pushing up against this, that we have really good methods for constraining many cosmological parameters. Most or all cosmological parameters are constrained at least to several percent, some a lot better. Okay, so first idea you might come up with for constraining cosmology with FRBs is to do essentially what's a Hubble diagram. We call this in our field the Makar relation, after this paper that initially did it with 8 FRBs by the ASCAP Craft collaboration. And so essentially on the x-axis, you is velocity or redshift, they're the same. And the y-axis is dispersion measure, which you can essentially think of as distance in a Hubble diagram. And so this was done, this diagram was made with 8 bursts in 2020, and it's improved steadily by various groups. And so for extracting cosmology from this diagram, there's an equation at the bottom of this slide that shows the expectation for a homogeneous universe for how much the contribution to the dispersion measure you have out to a given source redshift for the FRB. And so most of this term just depends on cosmology. There's the small fraction, this omega stars plus H1, that's not probed by plasma dispersion, the neutral gas and gas that's in stars. But I can believe that we can model that to a percent or so level. The part that's worrisome about doing cosmology with this type of diagram is the second term in the equation. This is the contribution from the host galaxy. So FRBs come from biased regions in the universe, the dense regions in the universe. And in order to be able to do competitive cosmology with this relationship, we really, at the percent level, need to model the second term, like to make statements about, for example, the Hubble tension, probably that are helpful. We really want this to have an error of about, or to know that term to about few percent. And I think it's kind of, it's hard for me to believe that we'll ever be able to do that. So I'm not super optimistic that we're going to make a lot of progress with this type of approach to FRB cosmology. Of course, at the end of the talk, if you object to my statements, and I'm going to make some opinionated statements such as this one, I'm happy to discuss. Okay, so if we're not going to be able to do cosmology from the mean dispersion measure to a given redshift, the next idea you might think of is, let's say I map many dispersion measures to many FRBs where I kind of know their redshift, or I know their redshift, maybe just with photosees. Then I just correlate the dispersion measure between the different FRBs. Well, this is going to be sensitive to large scale structure, because if I have a big structure, my dispersion measure for a couple of FRBs may go through the same structure. And so when I correlate the dispersion measures, essentially, this is a large scale structure survey. It actually is a large scale structure survey that's very similar to weak lensing. Where with weak lensing, rather than dispersion measure, you measure the shear of your background galaxies. And dispersion is giving you the total column of electrons. Shear gives you the total amount of matter, essentially, along that sight line. So we can compare the two, because we're actually in this era of weak lensing surveys. And so with modern weak lensing surveys, such as Rubin LSST, we're talking about 1 billion or probably 10 billion galaxies where we're doing this type of mapping of measuring the shear. The error on the shear for each galaxy turns out to be a bit larger. There's a lot of text here, and I'm not going to go through it carefully. The error is a little bit bigger than I would estimate for FRBs, but nevertheless, we're using at least 1 billion galaxies. And so if you just kind of do the back of the envelope, I think you need 100 million FRBs for this to start to be competitive. And at the same time, the FRBs are mapping the baryons. And the baryons turn out to be kind of the messiest, we think, part of large scale structure, messiest part. And so maybe this isn't 10 to the 8 FRBs is a lot. It's the baryons. We're already doing this with weak lensing, so maybe this isn't the way we want the path forward to cosmology with FRBs. Okay, and as you're going to see during this talk, we're often going to take ideas and keep trying to improve them. Maybe we don't have to map large-scale structure at the precision that you need for precision cosmology. Maybe we could still facilitate cosmology constraints. And so in particular, it turns out that with weak lensing surveys, and essentially like somehow the field of cosmology has invested humongously in these surveys, such that most upcoming cosmology surveys are of this sort, and like a bunch are listed here, including LSST and Roman. It's Euclid, and so the cosmologists have put a lot of energy into weak lensing. And when we were making forecasts for weak lensing, we actually didn't realize that the baryons are as terrible as they are. And so this movie from the Lustrous simulation is just showing you like how messy the physics of the baryons are. The galaxies are forming in certain parts of the universe. The explosions are the supernova and the AGN that are going off in those galaxies, and they're moving the baryons around. And so it turned out that when people made forecasts for all these surveys, the forecasts are wildly or way better than we have been able to achieve with these surveys. And it's because of this limiting factor of knowing where the baryons are. And so potentially FRBs could be used to help here. They could be used to map the baryons. You don't have to do this at high precision as you do for constraining precision cosmology, and it will help these surveys. And people have started to do this. I think the most promising way to do this is to correlate foreground galaxies with FRB dispersion. We did this, or my student and I did this a few years ago on Chime DR1. There's a really interesting paper that's going to be presented later in the week by the Chime collaboration, Wang et al. That did this on Chime DR2. I would say that the constraints are already getting interesting for help facilitating these weak lensing surveys. There's also been a lot of interesting work that you're also going to hear about this week on using the scatter in the dispersion measure redshift relationship to constrain baryons. And this is looking to me, I was originally kind of pessimistic about that type of approach, but I'm gaining some optimism based from some of this work that you're going to hear about. Okay, and here's just a cutout of all of the talks you're going to hear during this conference on this topic. If you're constraining the gas in the CGM, this is the gas that also we want to know where it is for constraining cosmological parameters. Okay. So now I'm going to talk about constraining cosmology from FRB timing, which is potentially the more exciting route, but where our ideas are less developed. Most of the ideas I'm going to talk about are going to involve strongly gravitational lensed FRBs. There's this really nice paper by Connor and Ravi that motivates that in the future, when we have tens of thousands, hundreds of thousands of FRBs, we should expect a lot of strongly lensed FRBs. Okay, with strongly lensed FRBs, the first idea you might have for constraining cosmology is that if you're able to measure so it's strongly lensed, so it has a bunch of it's going past a galaxy or a galaxy cluster, and this is creating some number of images, and so if you measure the positions of those images and you measure the delay, the arrival time delay between the different images, you can show that this can break the degeneracy between the mass of the lens and the Hubble constant, and so you can measure the Hubble constant if you assume that you know the mass profile of the lens, which is a big if. So you can do this with FRBs. You can measure the Hubble constant. Currently this is done a lot with AGN. The potential advantage of FRBs is that we can time them much better than AGN. So maybe this is the path forward. We'll do this arrival time lensing cosmology, but we'll just do it better because we can time FRBs better. Unfortunately, I think the consensus of people who've thought about cosmology from this type of probe is that what's dominating the uncertainty is not how well we can measure the arrival times of AGN, or FRBs. It's actually the potentially more complicated mass profile of clusters and galaxies, that galaxy lenses, than people have assumed in the past. And so, unfortunately, because timing is not doesn't appear to be the limiting factor, FRBs don't appear to me to be a huge advance over doing this with AGN. There's an interesting paper that acknowledges this and says, okay, maybe we don't use galaxy or galaxy cluster lenses, and instead we use stars. So stars we're going to start to see strongly lensed FRBs by cosmological stars in for example, the halos of galaxies. And then it's a point mass. And so I don't have to model the mass profile of my lens. And you could do this as long as you can also identify the positions of the images, so the angle from the point mass of the images. And so this paper by Tsai proposes that you can use scattering, where you get, as we saw, an AU scale telescope in effect to potentially measure the positions of the images. You need to do this at the percent level because we're doing cosmology, or maybe fewer, 10%. But if you can do that, then that would be a way forward. Okay, so we're iterating on this. So maybe galaxy and galaxy cluster lenses is for just time delay cosmology is not the way to go. But what if we measure the delay between two images, and then we wait some time? The universe has expanded by some amount over that time, and then we compare the difference in time in the delays between the two images. The formula is wrong. H naught should be to the -1. This formula is just the estimate for how much if I wait a time delta t, and my images are separated by some number of days in the right, it's evaluated at 10 days. Delta t times H naught is just how much the universe has expanded over a time delta t. And so if I wait a year, you just do the back of the envelope, you expect that the time delay between the images to change by 10 to the -4 seconds. 10 to the -4 seconds, that's of order the duration of an FRB. We could potentially measure that. If we measure that, and this is the only effect, we would be able to constrain the cosmology, because this depends on the expansion of the universe. Unfortunately, I think this doesn't quite work. It would be super cool to measure this, first of all. And in order to measure this, you need a lens repeating FRB. For a lens repeating FRB, the fraction of FRBs that are repeating is a small fraction of the total number of FRBs. And so we're starting to get into territory where it's not totally obvious that this source exists. But if it exists, and we measure this, it's part of the signal in the change of arrival time of the images is telling us about the expansion of the universe. That's amazing. But it also turns out that if you just back of the envelope for how much you think the mass of the lens grows, you'd write down the exact same estimate. Like the mass of your lens should also be growing on a Hubble time of order. And so to me, it doesn't seem like this is a precision cosmology probe, although super cool. Okay, so we're going to keep iterating on this idea. So rather than the change in arrival time of images, we're now going to talk about the change of the change, or the change of the change of the change, or just some power spectrum of I measure the arrival time difference and I take some power spectrum of it. And so what could this be sensitive to? Well, this could be sensitive to small things that are changing on the time scale that you're measuring the change of the change over. And so for example, in this image, it seems like the dominant effect could be that dark matter we expect to be very clumpy in the universe, to clump down to very small scales, Earth mass scales for WIMP dark matter. And so if this could potentially be sensitive to dark matter halos drifting across the line of sight, and in particular, how far a dark matter halo drifts over year time scales is about 100 or 1,000 AU. And so dark matter halos that have scales of 100 or 1,000 AU. And so we did some back of the envelope estimates to see if this could be interesting. And so our conclusion was that if you could do coherent timing, so if you could time these changes in the delay, the delays between the images, on the nanosecond time scale, then this is potentially sensitive to the amount of clumpiness that we expect for just vanilla cold dark matter. And there are a lot of dark matter models where dark matter is clumpier, like some of the axion models where the axion is formed after inflation, the condensate. So maybe that's the thing to do if we are able to discover a lens repeating FRB, and if we're able to coherently time it, which probably means that we have to be able to measure it at relatively high frequencies, like several gigahertz, then the time delays of the images will change in a stochastic manner that depends on the structures that are drifting between us and the FRB. And I'm probably going too fast. How much time do I have? 7 minutes, okay. All right. This is my last, oh, no. Oh, I actually have more slides than I realized. Okay, 7 minutes is perfect. Okay, another direction to go. Maybe we don't want to constrain the standard cosmology. Maybe we want to constrain more exotic things. And so the early universe can produce things like primordial black holes and cosmic strings. And so we can use the lensing of FRBs to place constraints on the formation of these objects. And so there was really interesting work led by Calvin Leung here that used the CHIME data set to do just this and actually did coherent timing. And the constraints are shown here. So so they were looking for small offsets in the arrival time from different images of a lens FRB, where it would be lensed by one of these primordial black holes. And they were sensitive to mass scales of 10 to the minus 4 to 10 to the minus 2 solar mass. And you can see their constraints on the left. It depends slightly on what they assume about scattering in the host galaxy. The constraints aren't quite competitive with macho surveys, which are most of the contours that are in the plot on the right. But there are going to be a lot of FRBs in the future. So this is something that definitely FRBs are going to contribute our understanding to. So constraining the mass in primordial black holes in this mass range. One in these plots is if all the dark matter is in primordial black holes of that mass. Okay, cosmic strings is another thing that could be produced in the early universe. And actually, there was a flurry of activity several years ago when PTAs announced a discovery of a stochastic gravitational background, a punitive discovery, that background could potentially be generated by cosmic strings. Currently, the cosmic microwave background rules out cosmic strings that have a tension. So tension is the string tension is the one parameter that characterizes these defects that can be produced in the early universe. So tension is greater than 10 to the minus 7 in these Planck mass units. So you can calculate what is if a FRB is lensed by a cosmic string, what is the delay between the two images, a typical delay. And so for G mu 10 to the minus 8, an order of magnitude less than what has been probed, the delay is 500 seconds. So that's a very reasonable number. And so with my collaborator, we did forecasts and laying die. And what we find is that around 100,000 FRBs, we're starting to probe string tensions that are close to the tensions that are the CMB is ruling out. And as we go into the millions and the tens of millions, it could get really interesting. And we could probe this parameter space to tensions that are much smaller than we have currently been able to. Okay, and then this is my final slide before the conclusions, and also maybe the most out there. So all of the timing applications that I mentioned involve lensing systems that we're looking at the different images and when they arrive. But you could imagine putting your telescopes far enough apart and timing the arrival of your FRB at the different telescopes. And so you can ask, like, what the heck would this give you? Well, the wavefront that arrives at your telescope when your telescopes are far enough apart starts to become sensitive to the curvature of its curvature. The curvature, if I measure the curvature of the wavefront, it's telling me about the distance to the FRB. In order to do this, you need 4 telescopes for the same reason you need 4 GPS satellites to measure the location of your phone. But if you have 4 telescopes that are separated by 40 AU, so I'm looking at the equation at the bottom of this slide. And you're looking at an FRB at 200 megaparsecs, and you're observing at 4 gigahertz there's a reason you need to observe at slightly higher frequencies that I'm going to get to than is typical. And if you're able to time to about the inverse of the frequency, then you can constrain the distance to the FRB by measuring this curvature of the wavefront with these 4 telescopes to about 2%. 2% is how well we've been able to constrain distances with supernova. So, and the reason I chose 200 megaparsecs is 200 megaparsecs is the mean distance of supernova in the SHU survey, which is this one of these surveys that is in this Hubble tension fight. Okay, so you could ask, okay, how crazy is this? I would say that a lot of things about this actually work. You would do this to repeating FRBs. And because then you would know where to point the telescopes. The most repeating FRBs, or a lot of repeating FRBs are at distances that are really good for this, 100 to 1,000 megaparsecs. The short duration of FRBs is actually really good also for this because you can actually send the data back to Earth, which is a problem if you were sending like a huge voltage time series. You can use large telescopes on Earth to try to pull out the signal noise on your to pull out the waveform from your distant telescope at the outskirts of the solar system. I think the biggest issue with this is that you need to go to relatively high frequencies because here I'm assuming that I can time to the inverse of the frequency. And so if you just take the scattering times from for example, Cordes and Lazio, for frequencies below 4 gigahertz, the scattering times are longer than this delta t. At about 4 gigahertz, things become refractive, and the refractive time delays become short enough that this error, I think, is realistic. But then there's the question: how many FRBs can we find at these higher frequencies? And so, with the remaining minute, I'm just going to conclude. Safe bet, FRBs are going to contribute to constraining cosmology via figuring out where the baryons are and facilitating weak lensing surveys. And I think we're already at the cusp with some of the work that I presented from Chime collaboration of this being interesting. The timing is potentially more exciting and more ambitious. The detecting lens repeating lens FRBs would be wonderful. Lens repeating FRBs would be really wonderful. It's not totally clear if this will contribute to standard cosmology for the reasons that I mentioned. FRBs will contribute to constraining these exotic relics, cosmic strings, and primordial black holes. And maybe at some point we can do something even more ambitious. Thank you.
Thanks a lot, Matt. We have about 4 or 5 minutes for questions. And please encourage the ones in the background because I really want to throw this.
Raise your hands. It's floppy and soft and light, so don't be afraid. Okay. Sorry, Matthias is farther away, so you're gonna go for that.
Oh, that's wonderful.
Excellent talk. This is Matthias. I'm a grad student at U of T. I was just wondering, what would you say is kind of your estimate for a timeline with which we could have a space-based kind of solar system-wide VLBI array? Your best guess.
Especially with current funding and what I will say is that the technology that's involved is not that much different than a GPS satellite. And so you need an atomic clock that's like on the atomic clock on our GPS satellites. You do need a big antenna. This radio Astron that Calvin even mentioned in his talk is a 10-meter antenna that was put into space. What I find is with 8 meters in space and 80 meters on the ground, you can get to 1 Jansky millisecond fluences for a millisecond FRB. So it's in the ballpark. We've discovered 5 gigahertz-ish FRBs that have those fluences. I would really like to know how, how many repeating FRBs one could expect. You need at least tens, I would say, for this to be worth it. I think we're at the point where it would be interesting to do some research, like the research into this, like where a high frequency survey targeting maybe the chime FRBs, I mean, it would be really interesting if there were repeating FRBs that were specific to higher frequencies that chime wasn't getting. But 10 years.
Okay, we're going for Robert. Matthias, it's your turn.
But going back to you or throwing over there?
We are going back.
Oh, back to Robert.
Not.
All right. Hi, it's Robert Main again. So I was wondering about the when you're measuring the time delays, which you said is not the limiting factor, either from lensing or when you're doing this like solar system wide VLBI. Are you counting on being able to actually coherently correlate the bursts? And then for the case of the solar system, I was wondering, like, are the different sight lines through the heliosphere, is that going to mess you up the same way the ionosphere does, or?
Yeah, these are really good questions. So it depends. I guess 10 to the minus 4 seconds doesn't necessarily require a coherent. And that's just for a year. If I waited 10 years, then it's a millisecond. I think the biggest problem for this, the change of the change, is that you need this to be coherent. And actually, so it turns out that for a lensing system where you're really kiloparsec or tens of kiloparsec size telescope, in effect, you really worry about also scattering in the host galaxy. And so I think that could put any scattering in the host, essentially for this idea, no, you can't have any scattering. Our galaxy becomes refractive, 3-4 gigahertz if you take nu the 4 scaling, minus 4 scaling. But yeah, so I think scattering is huge here. For this case, yeah, this is also coherent. That's why we're going to high frequencies. In this case, you don't resolve, but unless the scattering screen is greater than hundreds of parsecs from the FRB, you don't resolve the scattering screen in the host. And so here you more worry about scattering in our galaxy.
We have maybe Zoom question.
Kriti Sharma, do you want to unmute?
Yeah, hi. Thanks, Matt, for the amazing talk. I haven't thought a lot about timing yet. I just wanted to ask for like measuring change of change or just the change in the time delays. What's the observable that we are looking for, like in terms of modeling? And for example, in case of feedback, we have several models, right? And we are sort of limited by that as well. So what kind of limitations can we expect from the modeling front?
Yeah, okay, that's a good question. And so like you could partly think of this as like a Taylor expansion, that like the first is just linear and the time delay for us to wait. And then you'd have a quadratic term that the quadratic gets rid of anything that's on a really long time scale. So that's what we're doing. Like, because the linear term was dominated by things like the Hubble expansion and the growth of the lens, which occur on cosmological timescales. And so the quadratic is actually dominated by really small things that are moving across your images. You can also think of it as a power spectrum. Because it turns out that not only is it interesting to do the quadratic and the cubic, like everything is kind of interesting there because it's probing different size structures crossing your lenses. And so the paper considers both of those. So that whether there's a different way of thinking about it, like those are the ways we thought about it in that paper. And so yeah, so then you'd measure this term, and then you'd ask, how much clumping do I need along the line of sight in order to explain it? And I guess one thing I didn't mention is that there is a little bit of modeling uncertainty here, like even for like WIMP clumping dark matter, how what we're talking about is like the gravitational time delay between us and the FRB, and so there's some modeling there, that nonlinear modeling that you have to do to make statements like WIMP dark matter will produce this amount of gravitational time delay. Axion dark matter, which has more clumping, will have this time delay. So there's a modeling aspect, kind of like the feedback at the end.
Gotcha. Thank you very much. So for axions, can we also like put computative constraints on the axion mass? Like the particle mass?
Yeah, that's right. That's a good question. We were thinking of the QCD axion actually, and so there's some range of mass that's motivated. And the range of mass actually affects the size of these fluctuations, because whether these axions are generated by the misalignment mechanism or cosmic axion strings, I'm not going to get into. So it does constrain the mass, for the axion.
Gotcha. Thank you.
This is not the fuzzy like pseudo axion type of stuff people have been doing. It was the QCD axion.
Gotcha. Thank you.
You're welcome.
Time for one quick question. Maybe we can change speakers in the meanwhile.
Barak Zakai asking. So it seems that the property of the FRB that you are using in this particular idea is only the fact that it's compact. Aren't there compact radio sources that you could that are constant that you could use with this, so that maybe even one satellite that is just moving through the solar system will just map the distance?
Yeah, this is really interesting. So we started that's right. Not only is it compact, but you want it to be point source for tens of AU baseline. So so it has to be really compact. And so the paper kind of goes through different radio sources. Even black hole shadows are kind of marginal. Like the FRBs are really compact. Like we even saw that with millisecond scattering, with the scattering screen hundreds of parsecs from the FRB, they were still like AU type of like the angular extents. And so at least our contention was that they were the most compact thing that you could really do the only thing that was point source like that, where so the black hole shadows we would even resolve with these baselines. So I think FRBs are actually special. They're more point source like than anything else that we can imagine that we can see at extragalactic distances.
Okay.